shear force and bending moment diagram. So let us start. When a beam is in equilibrium under various forces and is cut at a section XX, prior to the cutting, there will be a force acting adjacent to the section, that is XX. The force is Fx, that is acting tangentially to the beam. Here is R1, reaction force, W1, W2, W3. These are the various forces that are acting on the beam. R2 is the reaction force, and this is the left side of the beam over which a force Fx is acting. This is because of due to resistance offered by the body. It means that Fx is produced because of due to the adjacent of material. The force acting by the adjacent of material. This Fx is a shear force. Now the sign convention of this shear force. So left side of this beam is considered as a positive if this shear force is downward, and right side of this section is considered as a positive upward forces. Upward forces is taken as positive forces, and here downward force is taken as a positive forces. And negative downward forces is taken as negative forces, and here downward force is taken as a positive forces.
So please write it down.
So shear force and bending moment. Okay. Shear force and bending moment. Diagram. Of cantilever beam. Here a sign convention. You have listen here. Sign convention about beam. Now the sign convention of bending moment. Bending moment. Sagging. If it is sagging type, it is taken as positive. Sagging movement is taken as positive movement, and hogging movement. Hogging से it is taken as negative. Okay, so this is a positive. If shape of the beam is like this, then it is a sagging, that is taken as a positive movement. If shape of the beam is like this, then it is taken as negative movement. That is, movement is acting like in this direction, movement is like acting in this direction, movement is acting in this direction. This was the sign convention that was taken in shear force and bending moment diagram. Everyone have to remember this sign convention, shear force and bending moment. So next, I would like to drive and shear force bending moment diagram for a cantilever beam point load at a free end. So shear force bending moment diagram. This is a cantilever beam. Cantilever beam. The one end of beam is fixed, other end is free. That is a cantilever beam. Here I am applying a force W on this beam. The length of beam is L. The length of beam is L. This is A point, this one is a B. Let us consider an section XX at a distance X from the free end. The shear force of this beam section between XX and B, the shear force will be shear force at section XX. Fx equal to W is a constant and acting downward force to the right side of the section is taken as negative. It means minus kW. This is a constant value. This is a constant value. It means throughout the beam A to B, this value will be constant. Hence, FB at point B, that is x equal to 0, FB equal to 0. Oh, sorry. FB equal to minus W and FA equal to minus KW. FB and FA. So we can draw the shear force diagram of this beam. Shear force diagram. Upward side is taken as positive shear force and downward side is taken as negative shear force. So here is W is FB. The load is acting downward, that is load is negative. It means this is suppose W. This one is a W. At point A, this load is also W. So there will be a constant line. This is a shear force diagram of cantilever beam. This one is negative. This is this is AB negative. Shear force diagram. It's a very simple case. And now I would like to try for the bending moment diagram. Bending moment diagram. Mx equal to Mx means bending moment at a section XX. That is, it is a x distance from free end. So the bending moment of B, tendency of this load is rotate clockwise. The shape of this beam will be like this. That is hogging. It means a negative bending moment. Minus W into X. Bending moment. That is force into perpendicular distance. Minus W into X. This is a linear relation. Linear relation. We can compare y equal to mx plus c, where c equal to 0, so w into x. And by putting the different values of x, we can find at different locations value of movement. Let us put x equal to 0, that is the bending moment at point B. So MB equal to minus w into 0, that is 0. And bending moment at point A, that is x equal to L, MA equal to minus W into L, that is minus WL. So it means the bending moment of cantilever beam is 0 at the free end and maximum at the fixed point. There is 0, and this bending moment, nature of this bending moment is negative. The negative is we have to draw downward. Minus W into L. This is it. This one is again negative. This is negative. A, this is B, bending moment diagram. So in this way we can draw shear force and bending moment diagram of a cantilever beam for various forces that are acting over this. I am going to write another expression for the shear force and bending moment diagram for UDL case. UDL case. UDL means uniformly distributed load for the cantilever beam. Uniformly distributed load. It means the load is uniformly distributed throughout the distance. That is W unit per length. Per meter. This is A, this one is B. Total length of this beam is L. Length of beam is L. W is the force intensity, that is W per unit length. The force is acting per unit length, that its value is W. The total weight of this beam will be this value, that is W into length. Total load, what will be the total load? Total load equal to, this is the total load. Now again we will consider a section XX at a distance x from free end. At this section we have find out the value of the shear force and bending moment. So first we have to find out the shear force, that is Fx. Fx means shear force at section XX. What will be the shear force at section XX? Yes? Very nice. Fx equal to, this will be the downward force. The total force is acting downward. It means the total value will be minus K W into X, because this length is L, X, and intensity, force intensity is W. So W into X, this is acting downward, and downward force is taken as a negative force. So this is a linear relation. Linear relation. Okay. This is equation number first. Linear relation because the power of x is 1. Okay. By using this equation we can find out the load intensity or shear force at different portion of this beam, that is A and B. Means at point A, x equal to L and F A equal to minus WL. At point B, x equal to 0, F B equal to 0. Hence the shear force at point B is 0 and the shear force at point A is a maximum, that is WL minus WL. So we have to draw the shear force diagram here. This is A and this one is B. Shear force is 0 and there is a linear relation between the force and load. Value of shear force at point A is minus W into L. W into L. Okay. W into L. This is W into L. So this is again negative shear force. Negative shear force. I am going for this is a shear force diagram. Shear force diagram is a shear force diagram. This is a shear force diagram. I am going for a bending moment diagram. For bending moment diagram, Again, you consider the same section at a distance x from free end. Mx, this is bending moment, or bending moment diagram. Mx equal to means a bending moment at section x. What is the moment? Moment is the force into perpendicular distance. What will be the force? Force is W into x. W into x is the force. W into x is the force. Into what is the distance? Distance will be where is the CG of this load? The CG will be at midpoint. Midpoint means that is at a distance x by 2. Okay? X by 2. Just multiply x by 2. This will become wx square by 2. Whether it is a negative or positive, it will be negative because its shape is foggy. Tendency of this force is to rotate clockwise. That is, the shape is foggy, it is negative. So write the sign negative. It will be minus k wx square by 2. This is a parabolic. Parabolic relation. Parabolic relation. You can compare y equal to mx square. Again, we can find out the bending moment at a different section by putting value of x. At point B, at point B, x equal to 0. Just put the value of x equal to 0 in this equation, equation number 2. This is equation number 2. So MB, that is minus kW by 2 into 0, that is 0. Bending moment at point B is 0. At free end, B is 0. The bending, another point that is A, extreme point A. At point A, bending moment. A means x equal to L. X equal to L. What will be the bending moment? Ma equal to minus kW L square by 2. Here I have to draw the bending moment diagram. At this point the bending moment is 0. Here the bending moment is minus kW L square by 2. This is a parabolic relation. Just curve shape. This is a negative. This is a negative. I think you understand this question, how to draw the shear force and bending moment diagram. This is the beauty of this question. How easily you can draw the shear force and bending moment diagram. After this lecture, you can easily draw for various forces also. Not a single force, but various forces. Suppose 2, 3, 4 forces you can calculate. Now I would like to draw shear force and bending moment diagram for a UVL case. For UVL case, UVL is uniformly variable load. UVL, shear force bending moment diagram for the third case है UVL, uniformly variable load. Uniformly variable load, for that this is the cantilever beam. This is A point, this one is a B point. The force is acting downward. I am considering only downward forces. It may be upward force also. that you have to consider this is a downward force. Here is W per unit length intensity. Here the load is varying from 0 to maximum W intensity. Here is the load 0 and here load is W. So how to draw the force and bending moment diagram of this type of question? That is, this is L, this one is L, this one is L. The length of beam is L, and now consider the XX section at a distance x from the beam. This is one type of a typical question. How to find out the shear force and bending moment diagram? We know that for triangle, the weight is area of this triangle. If you want to find out the weight of this figure, you have to find out the area of the triangle. The total weight equal to W into in terms of L by 2. This is the total weight that is acting over this beam A and B. So we have to consider only this portion. So first we have to derive a relation for this. Suppose this one is a y, this one is a y distance, this one is a y distance, this is x. There is a similar triangle. This is a small triangle and this one is big triangle. So there is a relation between similar triangle, small triangle and big triangle. Y upon W equal to x upon L. Here y equal to W by L into x. You have to find out the relation because we don't have idea of what is the intensity of the load at this point. So by this relation you can find out the intensity of the load at this point. So y equal to W by L into x. Now we have to find out the shear force at section XX. Shear force at section XX, that is Fx. Fx equal to, it means the load acting right side of this section. Algebraic sum of all forces acting right side of this section. So only one force, this is a uvial, is acting over here. So it means I have to find out the value of area. Area means y into x by 2. This is area and minus. And put the value of y from that relation. So y means W upon L into x by 2. That is minus k W x square by 2L. This is the parabolic relation. Question number first. Parabolic relation. This is a shear force at section XX. We can find out different shear force at different places by putting the different values of x. Put x equal to 0. It means at point B, x equal to 0. At point B, Fx equal to F means Fb equal to, put the value of 0 over here, minus W upon 2L into 0, that is 0. The shear force at point B is 0. And similar manner, put the value of x equal to L at point B. At point B, x equal to L. So put this value in this equation number first. So you have to find out the shear force at point A, minus KW L square upon 2L, that is minus K double L by 2. F equals. Draw the shear force bending moment diagram of this beam. Here is 0. Here is minus KWL by 2. This is parabola, not a straight line, but a parabola. This is a negative. This is a negative shear force. This is a negative shear force. Okay. In the whole beam A to B, the shear force is negative. And now I have to find out the bending moment diagram. How to draw the bending moment diagram of this beam? There it is. Now the consider section again XX at a distance x from B. The bending moment diagram for bending moment diagram. For bending moment diagram, at XX bending we have to find out the bending moment diagram. Mx equal to force into perpendicular distance. Force into perpendicular distance. So what is the force? We have calculated the value of the force. This is the value of the force, that is minus KW x square by 2L. Minus KW x square by 2L. Minus W x square upon L. Now we have to, this force is clockwise. It is rotating this beam clockwise direction, so this bending moment will be negative. So what is the moment? Moment is the force into perpendicular distance. Where it will be the centroid of this figure? It is at a distance 1/3 from here. This is x by 3, and from here 2x by 3. 2x by 3. So we have to multiply here into x by 3. This will become minus KW x cube upon 6L. This is equation number 2. This is equation number 2. And now this is a cubic relation. This is a cubic relation. What we conclude from these three figures? The bending moment diagram, shape of the bending moment diagram. How the bending moment diagram vary in a point load, UDL and UVL. In point load, linearly it varies linearly, and in UDL it varies parabolic, and in UVL it varies cubic. X power 3. Yes, now we have to find out the different values of bending moment at different points. First we have to find out at point B the bending moment, that is x equal to 0 at point B. That is MB equal to 0. Because if x equal to 0, the whole value of this equation will be 0. So W into 0, that is 0. If x equal to L, that is, we are talking about point A, that is at the extreme end, fixed end of this beam, cantilever beam. So x equal to L, what will be the bending moment diagram at section A? So M equal to minus KW x with the value q upon 6L, that is minus KWL square by 6. minus WL square by 6. As today we have discussed on the cases of cantilever beam, whether it is a point load, UDL or UVL. So in next class I will discuss about the simply supported beam, the shear force and bending moment diagram of simply supported beam. And the relation, I want to discuss something more about shear force diagram. In shear force diagram, we have seen that if load is a point load, then there will be a constant line. It doesn't vary. The load doesn't vary in between 2 points, whether load does not vary. And if load is a UDL type, uniformly distributed load, the variation of this shear force is linear. There is a linear relation between force and distance. And now in other last case, that is UVL. In UVL case, the shear force shear force vary parabolically. That is, it depends on x square. That is F proportional to x square. F proportional to x square. This parabolic variation. There is a parabolic variation between the force and distance. This is all about the cantilever beam. Thank you very much.